In this video, we're going to be learning one of the most important theorems in basic algebra, and that is the division algorithm. Every time we have two integers, a and d, where d is not 0, we can have guaranteed that there will exist a unique integers, and this is what makes this theorem so important, these two words, exist and unique integers, k and r, that satisfy that a can be written as k times d plus r, where r is a number between 0 and the absolute value of d. We're going to be calling these numbers k the quotient and r the remainder. Let's see, before proving this theorem, a few examples. If I take a equal 1038 and d equals to 14, then what I'm gonna have is that k will equal 74 and that r, the remainder, will equal 2. Why is this? Well, it's very simple. 1038 equals 74 times 14 plus 2. Now, this looks very simple, but what happens if instead of a equals 1038, I have that a equals negative 1038 and d 14? Well, we know, because of what we just saw, that 1038 equals 74 times 14 plus 2. So negative 1038 will be negative 74, and instead of plus 2, minus 2. And then you say, oh, okay, that's it. It's finished. I have my remainder and I have my quotient. We have a problem here, and it's that the remainder has to be a positive number smaller than the absolute value of d. And in this case, minus 2 is not positive. So we have to fix this. How do we fix it? Well, writing 74 minus 74 times 14 minus 2 is the same as if we add 14 and subtract 14, because this equals 0. So now rearranging this, what we get is that minus 1038 equals minus 74 times 14 minus 14 plus 14 minus 2. And this is minus 74 plus 14 minus 14 is minus 75 times 14 plus 14 minus 2 is 12. So then we found that k in this case equals minus 75 and the remainder r equals 12. Let's start with the proof for the existence. For this, we're going to consider different cases. The first one will be when a is positive or 0 and d is positive. And the intuitive idea of this case will be to consider numbers of the form a minus d, a minus 2d, a minus 3d, and so on, until we reach a certain number, a minus nd. And this n will be the one that satisfies that a minus nd is smaller than d, and greater or equal to 0. The idea is to prove that this number will be a remainder, and this n will be our quotient k. We need to formalize this idea. First, to formalize this idea, I'm going to introduce a notation. I'm going to call n sub 0 to the set of the natural numbers union the element 0. And now I'm going to consider the set A, which will be formed by all the numbers a minus j times t, where j is an integer, intersection this set and 0. Now it's clear that A is a subset of the natural numbers with a 0 because I'm intersecting them. And it's also true that A is different than the empty set because A is greater than or equal to 0, and so A minus 0 times t, 0 is an integer, so this element is in A, and then A minus 0t is A, so A is an element of A. So with these two properties, what we have is that A has a minimum element. Let's call this element R. R will be an element of A. And so there will exist an integer k such that R will equal A minus k times t, because R is in A, and A is formed by all the elements A minus jt with j an integer. So I know there exists this element k such that I can write it like this. Now this means that A equals k times t plus R. So we were able to write A as some integer times t plus some other integer. And this is exactly what we needed to prove. Now the only thing left would be we have to make sure that 0 is smaller or equal to R and R is smaller than t, because d is greater than 0, so t equals the absolute value of t. This first part is easy. R is greater than or equal to 0 because R is an element of A, which is included in the set of the natural numbers with a 0. Now to prove this second part, we're going to assume the opposite. We're going to assume that R is greater than or equal to t and try and reach something that's absurd. So if R would be greater than or equal to t, then what we would have is that R minus t is greater than or equal to 0. Now looking back, we can see that we have this definition for R. R equals A minus k times t. So we can write it. R is A minus k times t minus t. This would be greater than or equal to 0. And this is A minus k plus 1 times t, which is part of A. But this number, A minus k plus 1 times t, is r minus d, which is positive. So this is smaller than r. So we have an element of A that's smaller than r. And we said before that r was this minimum element. So this is not possible. Then r is smaller than d. And it's what we had to prove here. So we have now finished with the case 1 on our proof. Now the second case is when A is greater than or equal to 0 and D is smaller than 0. In this case, what we have is that minus D is positive. So for A positive or 0 and minus D positive, we have what we proved in the case 1. We know that there exist k prime and r prime, two integers, such that A equals k prime times the positive divisor minus d plus r prime, with r prime a number that's between 0 and the absolute value of d. And directly from this, what we get is that A equals minus k prime times d plus r prime. And all we have to do to prove our theorem is take k equals to minus k prime and r equals to r prime, and we get what we wanted. That's that A can be written as k times d plus r. And finally, the case number 3 is when we consider that A is negative. In this case, we have that minus A is positive, and so for minus A positive, we have the other two proofs we had before, so we know that there will exist k prime and r prime, two integers, such that minus A equals k prime times d plus r prime. Now multiplying everything by minus 1, we get that A equals minus k prime times d minus r prime. And now we're gonna consider two cases. The case where r prime is 0. If this happens, then all we have to do is take k equals to minus k prime and r, that will equal r prime equal to 0. And we have that A will be k times d plus 0. And we have proven the theorem. The second case will be when r prime is not 0. In this case, we will do what we did in the second example by adding and subtracting the absolute value of d. So what we'll have is A equals minus k prime times d minus r prime, which will equal, as we saw in the previous example, minus k prime times d minus the absolute value of d plus the absolute value of d minus r prime. And then all we have to do is take k equal to minus k prime plus or minus 1, depending on the sign because we don't know if d is positive or negative. We're doing this for both cases. And we are going to have to take r equal to absolute value of t minus r prime. Doing this will guarantee us that a can be written as k times t plus r. Now the only thing we're missing is we have to prove that this r is between 0 and the absolute value of t. Let's do that. We knew that r prime was a number between 0 and the absolute value of t. So multiplying everything by 0 will give us minus absolute value of t will be smaller than minus r prime, smaller than 0. And now we can add to every member absolute value of t. And this term in the middle is the way we defined r. And this will be greater than absolute value of t minus absolute value of t, 0, and smaller than the absolute value of t, which is what we wanted to prove. Now we're only missing one proof, and it's the uniqueness. So let's suppose that there exist k and k prime, r and r prime, all integers, such that we can write a as k times t plus r, and also as k prime times t plus r prime, where r and r prime will satisfy that 0 is smaller or equal to r, smaller or equal to r prime, smaller to the absolute value of t. Now in this part it's clear that we can do it without any loss of generality, because if it happens the other way around, then r and r prime are just general numbers in the integers, so it will still be valid. From this equal sign, what we have is that k minus k prime times t equals r prime minus r. Now this is very similar to one definition we've been working a lot with, and it's that the absolute value of t will divide r prime minus r, because it could be written as some integer times t equal to this. And as r prime minus r is positive, because we assumed that r was smaller than or equal to r prime, then if r prime minus r is different than 0, because of what we have seen in divisibility, we have that the absolute value of t is smaller or equal to r prime minus r. And as r prime is smaller than d, then r prime minus r will be smaller than absolute value of t minus r. And this is smaller than the absolute value of t, because r is a positive number. So this is an absurd. Then r prime minus r has to be 0, and this tells us that r is equal to r prime. So now from this equation we have that k minus k prime times t equals 0, and d is different than 0, so k has to be equal to k prime. and we were able to prove uniqueness. So the theorem was called algorithm. But what we've seen so far has nothing to do with an algorithm. Let's see how we can use the proof we just did to set up an algorithm. So we want to find K and R such that A equals K times D plus R. Okay, so if A is positive or equal to 0 and D is greater than 0, then you have to take K equals 0 and R equal to A. And what we will do is, while R is greater than or equal to D, we will do K, we'll redefine it as K plus 1, and R, we will redefine it as R minus D. If A is greater than or equal to 0 and D is negative, then apply the algorithm to A and minus D, and your response, the final result, will be minus K R. So what you do is you say, okay, I'm just gonna assume for the moment that D was positive. I'm gonna apply the algorithm for that D. I'm gonna do all this, and then I'm gonna have as a result, when R is smaller than D, I'm gonna have as a result KR, and that result will be for this pair of numbers, A and minus D. So the only thing you have to do is change your K for minus K and keep the same R. If A is smaller than 0, D is greater than 0, then apply the algorithm to minus A and D. Now if R equals 0, then your response will be minus K 0. And if R is not 0, then your response will be minus K minus 1 D minus R. This is what happened to us in the second example. And lastly, if A and D are both smaller than 0, then apply the algorithm to minus A and minus D. If R is 0, then your response will be minus K 0. And if R is not 0, then your response will be K plus 1 minus R minus D. Let's now prove a proposition. What we're gonna do is we're gonna call R sub t evaluated in A as the remainder of the division A divided by t. The first we have is that A will be congruent to R t of A, the remainder, mod d. Let's look at the proof. Well, by definition, the remainder of A will be the one we get from the algorithm. So we will also find a number k such that A can be written as k times t plus RT of A plus the remainder. Then A minus RT of A equals k times t. And this is the definition of congruence. A will be congruent to R d of A modulo d. The second, if A is congruent to R modulo d and 0 is smaller or equal to R, smaller to the absolute value of t, then the remainder will be this number R. How do we prove this? Well, A is congruent to R modulo d, so d divides A minus R. And this, using the definition of divisibility, tells us that A minus R equals k times t. So A equals k times t plus R. But if 0 is smaller or equal than R, smaller to t, then this R has to be the one we got from the algorithm. Then equals RT of A. The third part in the proposition says that if R1 is congruent to R2 modulo d, with R1 and R2 two numbers between 0 and the absolute value of d, then R1 equals R2. Let's prove this. We can write R1 as 0 times d plus R1, with 0 smaller than R1, smaller than d. Then the property 2 will tell us that R1 equals the remainder, the division by d of R1. And we also have that R1 is congruent to R2 modulo d. And R2 satisfies that it's between 0 and d. And then again, using the property 2, we know that R2 will be the remainder in the division by d of R1. So R2 is this and R1 is this, and this tells us that R1 equals R2. And now the final property, and the most important one, is that A is congruent to B modulo D if and only if the remainder in the division by D of A is the same as in the division of B. So to prove if and only if, we first are gonna prove the arrow that way. So this will be our hypothesis: A is congruent to B modulo D. And we know that A is congruent to the remainder A modulo D. This we know because of the first property. Now for transitivity and symmetry, something that we proved in a previous video, we can know that the remainder in the division by d of A will be congruent to the remainder in the division by d of B modulo d. But then the property 3 tells us that this equals this, because 0 is smaller or equal than both of the remainders, and they are both smaller than the absolute value of t. Now let's prove the other way. So now we are assuming that RT of P equals RT of A. This tells us that RT of A is congruent to RT of B modulo D. But then again, due to transitivity and symmetry, we know two things: that A is congruent to the remainder of A, and that B is congruent to the remainder of B. And then we get that A is congruent to B modulo D, which is what we wanted to prove. Let's solve a few exercises. The first exercise is to calculate the remainder of the division by 5 of A, where A is a very complicated number. Is 166 to the power 1328 times 4878 plus this very long number. Each number in A is congruent to its remainder. So 166 is congruent to 1 modulo 5. This number is congruent to 3 modulo 5. And this other very long number is congruent to 4 modulo 5. Then 166 to this power will be congruent to 1 to this power. This is a property we saw in another video, modulo 5. And now if we add all this up, we get that the number we wanted is congruent to operating with the remainders. It's 1 to the power 1328 times 3 plus 4 modulo 5. This would be congruent to 1 times 3 plus 4 is 7 modulo 5. And 7 modulo 5 is the same as saying 2 modulo 5. This tells us that the remainder of dividing by 5 this number A is 2. The other exercise will be to calculate the remainder of dividing by 35 the number A, where A is this other very complicated number. Now, sometimes congruence is stronger than thinking about the rest alone. So sometimes instead of replacing the numbers by its remainder, it's better replacing them by, if you can, for example, -1, or it's better observing some useful behavior. Here, for example, what we can observe is that 6 squared, which equals 36, is congruent to 1 modulo 35. Also, we can note that 34 is congruent to minus 1 modulo 35. So 34 to this very long number minus 6 to the also 1, I can write it as, instead of writing 1001, I can write 2 times 500 plus 1, which equals and now with this I can work with these two congruencies I found before. I will note that my number is congruent to 34 is congruent to minus 1, so I will have minus 1 to the power I have my 34 minus this minus we have from the operation 6 squared is congruent to 1 to the power I have times 6. So when we do these operations, we have this long number is congruent to minus 1 minus 6 modulo 35, and I forgot to write it here, modulo 35. Minus 1 minus 6 is minus 7 modulo 35, and saying minus 7 modulo 35 is the same as saying 28 modulo 35. And then with this we get that the remainder of dividing by 35, our very long number a, is 28.